Okay, just a quick review of what we've done. And remember, in the beginning we weighed out some copper. We added nitric acid to it in the hood. You saw a brown gas, and you created a copper 2 nitrate solution. Now this was what color? Do you remember? It was sort of a bluish color. Then you added to this, you added sodium hydroxide, and you sort of got a thick, pasty copper 2 hydroxide, which is a solid. Then you took this, you heated it, and you got copper 2 oxide, which was the black precipitate. Remember, it's settling out of the water. Then you went and added sulfuric acid, and you got copper sulfate, which was sort of a nice blue color. Then you added zinc, and you notice the blue color disappeared as the copper came out of solution. And any excess ink that we had thrown into the system, we destroyed using HCl by creating hydrogen gas and zinc chloride. So in the final rinse, there would have been zinc chloride, maybe some excess HCl, and maybe some copper chloride. Or not copper chloride, zinc chloride. So those would have been the waste products in that clear water liquid. Okay, this is the data I've obtained from this experiment. I started out with 0.585 grams of copper, and this is the evaporating dish. This is the weight of the dry copper. The dry copper, okay, when I weighed out my copper, it weighed 0.585 grams. And this is the weight of the evaporating dish and the dry copper. This is the weight of the evaporating dish. So the difference tells me how much copper is in here. If you notice, I got back more copper than I started with. So obviously, this must be divine intervention. Otherwise, that just would not happen. But in reality, probably means that when I washed my sample, I did not get out all the secondary salts out, like the zinc chloride and so forth. So those are in there adding weight. So that is probably why I came up with a wee bit more. When I took the percent error, I came up with a 1% error, plus or minus 1%, because when I took the difference between these, I only had 1 sig fig, so I could only report it as 1 sig fig. Again, it's reported as plus or minus, because it may be above the accepted value, or it may be below the accepted value. So.
Talk about that.
Okay. Okay. I will walk you through this is a molecular equation. This is the way you normally write equations, and 99% of the time is how you will write equations. But when we do net ionic equations, what we do is we take out all the spectator ions. We leave out them. So what I do, everything that's a solid, liquid, or gas, I leave as is. Anything that is aqueous, I put in ion form. So this was solid, so I'll just put copper. Now notice this is aqueous, so it's 4 hydrogen ions plus 4 nitrate ions. Now this was aqueous, so I put it in aqueous ion form. Notice this was a gas, so I leave it as is. And water is a liquid, so I leave it as is. Okay. So if you look at this equation, first thing you look for is spectator ions. Those are ions that are the same on both sides, identical. If you notice, I got 4 nitrate ions here, I got 2 there. So I can get rid of these 2 and reduce that down to 2. My coppers are different, my hydrogens are different, and so I cannot do anything with those. So my net ionic equation would be my copper plus 4 hydrogens plus 2 nitrates copper ion plus NO2 plus water. So this is chemically what happened. And if you notice, the sum here is 0 plus 4 minus 2 equals plus 2, 0, 0. and you can see right away, charge-wise, it's equal. So you can always check your work to make sure it's correct by checking the charges too. If there are no charges on one side, there should be no charges on the other side. So that's how you do molecular, ionic, and net ionic equations.